Hello, this is J.A. McDonald, and today I have something rather interesting for you. And no, this is not Minecraft, this is me making a program. Now, with this particular program, it will generate a maze. And you can see it running over on the right there. It just started making the maze. It had been laying down the noise map previously. So there we have a pretty good closed maze, meaning there is no entrance and there is no exit. Now this is not what you want for like a maze runner game or something, but this is exactly what you want if you're building some sort of arena or laser tag or boombox. And I am terrible at making these things, so I made a generator. Now quite clearly there are some errors in this, like right here is an inaccessible section. And here, this section never connects to that section. But you can easily fix those by deleting a couple blocks. So I'm just going to go through the code here, line by line essentially, and show you how it's made. First, let you see that go one more time. And while it's doing its thing, I'm going to amp up the size of it while I am walking through the code. So just watch the nice maze go for a second here while I get the rest over here. Another beautiful maze, still some inaccessible spots, but you know, that's okay. Okay, that should be good. So this is a huge maze. This is 400 or so by 400, and each block is a single pixel, so it looks quite grainy. Actually, I'm going to restart that with 2 blocks per pixel. That might be way too big. Yeah, that's too big. I'm going to go back to 1 block per pixel. Sorry, it's a little bit hard to see, but it will be worth it in later. And at the end, I'll take it into Paint and artificially enlarge it. So as that's going away, it has quite a few iterations because quite a few surface. Let's start at the top. The X size is quite clearly the X size of it in blocks, and the Y size is the Y size of it in blocks. Right now both are set to around 420 or so. Block size is the number of pixels in each block. As you see, it's set to 1. It's normally set to 10. Iteration. This is how many random times squares will be inverted. This should be fairly large, about 5 to 10 times as big as your X size multiplied by your Y size. Because it has to cover each pixel at least once, and it should go back and cover others several times to give it a nice texture. Smoothing here. This is how many times the final maze smoothing algorithm will run on it. Now, this can be fairly low. The lower the number, the more true to the original map it will be, and the higher number, the more regular. Now this thing will find its limit at some point, and it will stop smoothing after a point, but that can be a good thing. Sometimes it makes more dynamic mazes with a smaller number. So then here we have a state machine, right about there. All it contains is an update and an invert square method, which I was just using so commonly I figured why not put invert square here, and this just detects whether a square is black or white and flips it to the other state. Now it does this by adding this magic number here to the result. And don't ask why exactly. Okay, you can ask why. Basically, if you add, this is the value of black for some reason. Don't ask why on that one. I have no idea why that's black. But this plus this equals 0. White is -1, which would be a problem, except this thing takes into account larger numbers than -1 being -1, so that's fine, it's white. Now if we have white, we have actually -1 here, -1 plus that stuff is 1 more than that. So I suppose we could bump this number down and it'll be fine. And when you multiply that by -1, it goes past this black thing here and inverted. Ooh, we can see it smoothing right now. Oh, I love that. Inverted, it's, of course, black. So everything's fine. Then we just fill a rectangle of the right size, and that's all of our state machine. Now our first state here is actually our last state. This is done. It doesn't do anything. It just parks the code for when it's finished running. Now noise map here. You just saw that running for quite a bit over on the right. It generates a huge noise map. It just takes a random coordinate, multiplies it by the block size, so it's always in the middle of a block, and then it will invert it. So whatever color it used to be, it won't be that anymore. Then it increments it checks iterations, and if it's out of iterations, it goes to maze. At the end, it increases iterations, so this thing always runs twice, if I recall, at least twice, because it will go through here, and this condition won't be met, so it'll go again, and it'll go through here, and the condition still won't be met, but this condition now is, this condition is now met, so it exits, so it runs through it twice. And it exits into maze, which is this next class here, which does the actual smoothing over there that you're seeing going on right now. Now these two are just kind of other X and Y's, permanents. I couldn't exactly figure out what to name them, so old X and old Y had to do. Repetitions is an internal counter. Up here, it's named I. Why didn't I use I? I don't know. I'm not consistent, I guess. But yeah, repetition is our counter here. So now we take the old X value and we increment it because we're moving 1 across. And if that's big enough, we jump back to 1 because we're skipping the border and start doing the same thing to Y. When we get to the end of that, we increment repetitions 1 and restart. When we're done with all of that, we print out done and go to done. So that's all fairly simple. Now to figure out our real X, we take old X times block size, blah blah blah, and we want to get the middle of the block, so we add half of block size. Now I'm going to take a brief moment here to print my screen, and we'll go on over to Paint, where I'm going to paste my screen, crop it to the maze, and give you a amazing view. So let's just select the maze here. Come on. Select the maze and greatly increase its size. Now I've probably, oh, that's terribly skewed. I'm going to use the size increasing little widget thing. So resize by, let's go with 400. There we go. So that is what was generated by our maze machine, and I think that looks just amazing, if you'll pardon the pun. Yeah, that is just beautiful, and I really enjoy watching this program run. So I don't, let's cancel that. I do need this in the background still. So there's our maze. I'm now going to decrease this back to a reasonably sized maze, because hey, that one's a little big, and I have some quick exploits to show you in my coding. So where were we? We were here. So detect neighbors, this is an interesting function we'll get to later. But right now the piece of interest is this condition. Right now it's set to 2. And with a 2 value there, I forgot to change up the pixel size. There. So with a 2 there, it generates the normal maze we've been looking at. And you'll see that in a second over on the left. right as soon as that thing finishes generating. And for the purpose of these next few, I'm going to decrease iterations. So as you see, there's our normal maze. And it doesn't particularly tend towards anything. However, where'd that go? Here. If we change this condition down to 0, its minimum value really, anything less than that makes no difference, you'll see it just sits here inverting the maze. So 0 was a little bit ridiculous. Let's go to 1. What could 1 do? It should be right? No, basically detect neighbors tells me how many neighbors I have. And if I have one neighbor, then anything with a neighbor will do this. So the more iterations we run of this loop, the more we will tend to see perfectly straight, long lines out there. Now, we'll cap out at a certain point on a diagonal, because the lines will meet at a diagonal there. As you see happening over here, we have a nice diagonal. Then we have perfectly straight lines and everything else. More iterations should wipe it out to a nice diagonal there and possibly a diagonal here. Not entirely sure, but it might also wipe it out to pure straight lines. So that is very interesting. Now if we skip 2 and we bump it up to 3, it does other interesting properties of not changing the maze near as much as we might want. There it has more or less done all the changes it's going to do, which could be a good thing, but I don't think it is. On this particular map it's a good thing because we have such a low iteration of pixels. This might be a decent map to play on, but I like my other maps better, so I'm not going to bother with this type of generation. Now if we change this to 4, that means there's more than 4 neighbors, which by our current neighbor detection is impossible, so it will not change a thing. I'll go ahead and change this back to 2 and run it on the decreased iteration. And there we go. Not the great, pretty good maze actually. Now for the interesting bit, detect neighbors. This section of code down here gets ugly. So this commented out section of code here is designed to detect the neighbors that are directly adjacent. So if it was this block here, I think you can see my mouse, I hope you can. It should detect this block, this block, this block, and that block. So the final count will be 2 because this block and this block are the same color. However, it had problems of generating checkerboards instead of this pattern. Now, I don't know why that is, but if I check for the diagonal pieces, so that'd be here, 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 and here from this block, also yielding 2, then it yields the correct result. Now, I tried both, but it didn't work at all, even messing with the condition above here. So I'm not sure what's going on there, but this works. So then we go down here to noise map. This is the start of our program, really. It initializes our noise map as our state to noise map, and then it goes through the rest of our program, sets up a nice window the right size, turns the background to black, and then fills in a white square 1 block in from the edge, making a beautiful border. Now I turned stroke off here because it was getting in the way with the drawing of these things, because they would be 1 pixel too wide, which would freak out other things later. Now draw down here, I'm not sure whether it's 30 times a second or 60 times a second. Either way it's too slow, so I do 100 times of this per draw cycle, except when I do that massive grid, then I bump this up to 100 or even 1,000. But that makes it a lot better and still nice to look at. If I bump it up to 1,000 right now, you won't see anything. It just appears complete. So I'd do that if I was in a hurry, but I like watching it generate, so let's put another one of those on generating. So state update, this is the only real line you need in your program. It puts all the other classes into motion and everything goes good. Now this section down here is something unique to the program I'm using, which is called processing. Well, I suppose it's not unique to this, other things have it, but it's especially in this one. This is a interrupt on my mouse clicked, so if I click and release my mouse, it'll run another smoothing run. It's going to be useful if I get a maze where I don't smooth it quite as much as I want, or if I go up here and I turn smoothing down to 0, it will run only once. And if I want it to run more than that, I can just give a click of the mouse and it should run another time. It's a little bit finicky in detecting mouse clicks, but you know, better that than nothing. So let's just run this up to that and this to 2 for a final little test. I will be including a link to this code. Unfortunately, I don't think I can just post it in the description because I don't think YouTube likes braces. Either way, you'll be getting this code. It's designed to run in a program called Processing. I'll include a link to that in the description. And have fun. Use this to generate mazes all you feel like. Build them in Minecraft or other things. Whatever you want. This is made to be building in Minecraft, but who cares what it's made for? Always fun to take things and use them for what they were never intended. So I plan to build a maze generated from this thing in an upcoming build of mine. I don't think I'll give it away just yet, but I can pretty much guarantee that you will like the build. So I will see you next time I see you.